Everyone. Thank you for the introduction. Yeah, it's true that we have also been contributing to things related to the coronavirus, but given the current situation, I'm pretty sure that you are all fed up of listening to talk about distance, lockdown, isolation. So instead for today, I decided to talk about something different. Exactly, I will talk about the opposite. I will be talking about connectivity. And as you will see, or I expect to convince you, connectivity plays, or the way things are connected, plays a relevant role, a central role in condensed matter physics. And I will try to show you that there is at least a class of problems in condensed matter physics where the relevant questions can be reduced to a simple question. That is there global connectivity or not? And so because of that, I will be talking about the percolation model. That is a classical model in statistical mechanics that was introduced, at least in physics, more than 50 years ago, and where the idea is to describe connectivity in a very simple way. And so since this webinar is taking place in the context of a summer internship for undergraduate students, my goal today is to convince you that the answer to seemingly complicated problems many times relies on very simple models and assumptions. And so the key challenge for theoretical physics is to be able to identify what are the relevant mechanisms and what can be neglected when we try to model a system. And for that, let me start with a very simple example. So imagine that you get a gift from IKEA, okay? And when you open the box, you see no instructions. Instead, what you find is a set of building blocks, in this case, like the ones in this image, that are just stones. You know how many stones you have of each type, but the question is, what is the structure that you can form with these stones?
The image, Nuno.
Sorry?
I don't think we are seeing the image.
Let me stop the sharing and share it again.
Yes, now. Yeah.
Let me see if now it's working.
Yeah.
Okay. So as I said, so you got a gift. And so the question is, what can you do with these building blocks? Okay. In order, without instructions, will be difficult for you to try to understand what is the structure that you are supposed to build with these building blocks. It's only when you follow the instructions and then you connect the pieces according to the instructions that you realize that what you just got is the set of stones that you need to build a replica of Stone Age. And so what is relevant here, and the message that I'm trying to convey here, is that besides its history, what makes Stone Age so special, and in fact why it attracts almost 1 million visitors a year, is not the properties of the stones itself, it's not the material that they are made of or the shape of the stones, but rather the way that they are organized in space and connected to each other. And so this idea that the sum is different from the parts is a central idea in condensed matter physics. In physics, in condensed matter physics, what we want to do is to describe phenomena that emerges from the interaction between the building blocks. And the building blocks can be atoms, can be molecules, can be colloids, can be polymers, can be many different things. So what is interesting for describing the phenomena is the spatial arrangement and how the spatial arrangement evolves in time. And so, as you will see, in many of those problems, the relevant question is how, if there is global connectivity or not between the different pieces. In order for you to understand, let me show you some examples at different scales. Let me start with an example at the microscale. So imagine a certain material that is an insulator. For example, here I drew a schematic representation of a polymer network, okay? So it's an insulator. And the way experimentally to make this system or to change the electrostatic properties of the system is to embed gold nanoparticles into the network. So you can add some gold nanoparticles. And the idea is, above a certain concentration of gold nanoparticles, the distance and the spatial arrangement of the gold nanoparticles and the distance between the particles will be such that in a classical picture of electrostatics, if you apply a potential difference, electrons will be able to hop from particle to particle and find the connecting path between one side of the system and the other. And so the relevant question is, what is the amount of nanoparticles that is needed in order to guarantee connectivity between both sides of the system? Let me show you a second example, now related with cigarettes. In fact, it's related with filters, the filter of a cigarette, but is general for any type of filters. The filter, by definition, is a porous material, okay? Basically consists of open spaces that might be connected or not, might have different sizes. And so the relevant question for a filter, in the case, for example, of a cigarette, is what is the maximum porosity that we can have in the filter such that smoke or air can go from one side of the filter to the other, but we are still able to retain the toxic particles. So again, we have different units that now are the pores. And the question is how much they need to be connected such that we manage to find a connecting path between one side and the other. Well, but the challenge is to show you that this happens at different scales. So let me now go to the meter scale. And now imagine that you have a lake or a river, and you want to cross the lake or the river without touching the water. And if you have some stones on the water, above the water level, the question is, what needs to be the density of stones or the number of stones such that we can go from one side to the other by hopping from stone to stone? And so, again, the question is related to the connectivity between the stones. But there are other examples. For example, oil extraction. If you want to extract oil from a soil, again, the soil is a porous medium. And the idea is what needs to be the porosity of the soil such that drilling at a certain point, you will likely find a reservoir that is large enough such that becomes economically viable to extract oil from that region. Or you can go to an even larger scale and think about a forest. If you have a forest fire, what needs to be the density of trees such that if the fire starts at a certain tree, it will likely propagate through a large region of the forest and have a huge impact in terms of fire because the fire will jump from tree to tree. Or you can also think about the global scale. Imagine that you have your airports in the world, and you can ask what needs to be the average number of connections of an airport in order to guarantee that you have global connectivity. And here global connectivity will mean that you can take a flight from a certain airport and arrive to any other airport in the world, either through a direct connection or with a stopover in other airports. So from the point of view of physics, what we have here is, yes, it's true that the basic units, the building blocks are different. They can be nanoparticles, they can be pores, stones, trees, or airports, but the question is the same. What needs to be the degree of connection between these building blocks in order to obtain global connectivity? And as I said in the beginning, this is precisely the question that we try to answer with the percolation model. Let me be more precise about what we mean by the percolation model. So as a physicist, we always like to simplify. So let me start with a very simple configuration of our building blocks. In particular, I will be looking to, trying to get a pointer here. You can see my pointer? Yeah or no?
Yeah.
Okay, so my building blocks are here now represented in blue, and they are organized in the square lattice. So each one of them occupy a site on a chessboard-like configuration. And so initially, we have no connections between the building blocks. But now for each bond between first nearest neighbors, like for example, in the case of this building block or this site, it can be connected to 4 nearest neighbors. For each one of them, I will occupy the bond, I will connect the two building blocks with a certain probability P. So if P is equal to 0, there are no occupied bonds, all sites are disconnected, we have all sites isolated without any connection to the neighbors. If P is equal to 1, the probability with which we occupy the bonds, then all them are connected to the nearest neighbors. So you will find that all bonds are occupied. And in between, you find different configurations. And here I'm showing you an example for an intermediate value of P. So in red, I'm representing the bonds that were occupied with probability P. And so what you can see, you can even define a second quantity, or you can define an aggregate in the system as a set of nodes or of building blocks that are connected by occupied bonds. Like here, what I'm seeing is an aggregate of size 2. Here I have an aggregate of size 5. Here I have an aggregate of size 4. Here I have an aggregate of size 3. So an aggregate is a set of sites that are connected by or through occupied bonds. And within all the aggregates, I can identify the largest one, the one that contains more particles. And here I'm representing the largest aggregate in green. So this green aggregate is the largest one in the system. And if there is a connection between opposite sides of the system, typically this connection is established by the largest aggregate. So if you are thinking about global connectivity, one way to do that is to focus on the properties of the largest aggregate in the system. So let's see how the size of the largest aggregate scales or depends on the probability P with which I occupy bonds. So that's what I'm plotting here. On the vertical axis, what we have is the size of the largest aggregate, measured in terms of fraction of sides of the lattice that belong to the largest aggregate, as a function of P, the probability with which I occupy a bond. And so what you can see is that for low values of P, the size of the aggregate, the different lines are for different system sizes. I will not discuss the details, but for low values of P, what we see is that the size of the largest aggregate is practically negligible. However, as you cross this specific value of P, in this case 0.5, because we are talking about bond percolation, then the size of the largest aggregate grows as a function of the distance between the value of P and the critical value of P of 0.5 in this case. To be more quantitative, what you see is that the fraction of sites in the largest aggregate scales as P minus PC. PC is the critical value, P is the value of the probability, to an exponent beta. And this exponent beta is quite relevant for the problem because it's a universal in the sense that you can only change these, there are many ways to change it, but the value of beta typically only depends on the spatial dimension of the system. So if you do it in 2D, it will not depend on the lattice that you are looking at. It could be a square lattice, a triangular lattice, a bunch of points that can only connect to neighbors that are at a certain finite distance. In all those cases, if you do the same study, what you see is that the value of the exponent beta is the same. And is in fact the fact that this exponent beta does not depend on the fine details of the model that allows us to use the percolation model to try to get insight about all these problems that I have showed to you before as an example. And so another interesting property, there are many properties, interesting properties in this model, but one of them is that if you look to what happens at P equal to 0.5 at the critical value, you see that the size of the largest cluster goes to 0. Remember, the size of the largest cluster is the fraction of sites that belong to the largest cluster. And so if the value of the size of the largest cluster goes to 0, what that means is that the fraction of sites goes to 0. Doesn't mean that there are no sites in the largest cluster, but when compared to the system size, this is negligible. And this is interesting because when we look to a snapshot of the aggregate, of the largest aggregate at PC, we see that it spans the entire system. And so what this means is that the mass of the cluster scales sublinear with the volume of the cluster, and that's why the density is 0. And this is the typical property of a fractal object. So the percolation cluster at the percolation transition is a fractal object. And so, as I said, this model has been around for more than 50 years, but we can still find to you or something or any change on this model that might have an impact on statistical.
No, your internet is failing a little bit. Can you repeat what you said?
Let me show you two different examples of. Is now working? Can you see it now?
Yeah, it's failing a little bit.
Can you hear me now?
Yeah, I can hear.
Okay, is better?
Yeah.
I'm sorry for that. So let me show you two examples of problems where, or recent problems that we have been working on, where we keep finding surprising results about percolation. The first one was inspired by a movie. I think I'm having again problems with sharing the screen. Let me again. You know, computational physics, we have always problems with computers. Okay.
So we don't.
Anyway, I can. It's not working.
Yeah.
1 minute. Sorry for that. Okay. Can you see it now?
Yeah.
Yeah. Okay. So I was here. So the example that I wanted to show to you is related to a movie, Entrapment. I don't know if you have seen this movie, but basically the story is the movie has two famous actors, Catherine Zeta-Jones and Sean Connery, and in the movie, Catherine plays the role of someone that works for an insurance company, and Sean Connery is a thief, and so she's working undercover, and she wants to prove to Sean Connery that she's really she's also a thief, and so for that she plans a big robbery, where at some point during the robbery, they need to cross a room from one side to the other. But this room is full of laser beams, as you can see in this picture on your right-hand side. And so because of if she interrupts the laser beam, then this will trigger an alarm, and by triggering an alarm, they will be found. So the question is again a percolation question. That is, what is the number of laser beams that we need in the room to guarantee that you suppress connectivity from one side of the room to the other? However, this is different from the fundamental point of view from the description of the classical problem of percolation that I defined before. Before, what we were doing is that at each time we were adding a bond between the building blocks. While here, what we are doing is instead of adding a bond, we are removing bonds. And in fact, instead of removing one, we are removing an entire line of bonds in the system. And so since you remove a sequence of bonds that are aligned, you have some long-range correlations that are imposed by the fact that you are removing a sequence of bonds. And so even from the fundamental point of view, this is a very different or new addition to the model. And it's interesting to understand what happens to the statistics of the problem. And we found very different things. In particular, we found that this model shares some common properties with 2D percolation, with 3D percolation. In the case of 3D, it has the same, the percolation cluster has the same fractal dimension, but the value of beta is different. And so we found very interesting results, but we needed to report them to the scientific community. And we thought that maybe calling it Zeta-Jones percolation or connecting it to the movie will sound like not a serious problem of physics. So we took advantage of the fact that the model doesn't depend on the fine details. And therefore, we presented the model as a drilling percolation problem. So what we said is you have a wooden cube, and now you start to drill holes in the cube. And the question is, how many holes can you drill until the point that the wooden cube will collapse because you destroyed the inner structure of the wood. And as I said, what is so special about this model is really the fact that you take out an entire line of connections inside the cube. But you don't need to think about a straight line. You can think, for example, about the random walk. And this is the second example that I wanted to show to you. That is the example of a termite. Imagine that you have a wooden house. This is something that is quite problematic in Canada. And inside the wood of the walls, you have a termite. As the termite moves around, will eat or destroy part of the wood structure. And the question is, how long can you wait until the house will collapse because you destroyed the structure of the wood? And so this is again a percolation problem where the question is, if you have a Brownian motion, a random walk inside a 3D structure, you can ask, how does the connectivity between the parts that were not yet visited by the termite evolves in time as a function of the number of termites and things like that? And though this problem has been studied both by mathematicians and physicists, mathematicians call it interlacement percolation. The physicists like to call it Pac-Man percolation because it remembers the game, the arcade game Pac-Man. And the problem has been studied for more than 15 years. And up to now, things like what is the nature of the phase transition or what are the critical properties of the system are still open because, as you can imagine, there are strong finite size effects, even if you try to do simulations of this problem. So it's still an open question, and who knows if any of you will help answering those questions. So thank you for your time, and I think I'm done with the time, and I will be happy to answer your questions.
Okay, Nuno, thank you very much for your interesting talk. And we can have some questions on the Q&A. So we have the first question, which is an anonymous. Let me turn on my camera. So Nuno, your sound was a bit intermittent during the presentation, and I think people
Really?
understand the main message, but we can see from the questions what.
Sorry for that.
So an anonymous asked, so you say that physicists are always looking to simplify things and looking for the building blocks. My question is, when it's necessary to add more complexity to the problem? When is it necessary to add more complexity to the problem?
Okay, thank you for the question. Well, it's not looking to the building blocks, it's looking to the mechanisms, okay? It's like in a simple problem of physics. If you try to study the motion of an object that is falling, you drop something and you want to calculate, for example, how long it takes to touch the ground. Well, there are many things that you could consider. Air resistance, size of the room where we are, temperature of the room, and things like that. So what you need to do is to think about what are the relevant mechanisms and what plays a role and what can be neglected. If you don't know, what you can start is with a simple approach, see what you can say about the system using a simple approach, and keeping adding ingredients to your model. By doing that, you can do two different things. The first one is that you will be able to see what is the impact of a certain new ingredient that you added into the model. And the second one is that you will have an overall picture of the relative importance of each mechanism that you are adding to your model, okay? So when it's necessary to add more complexity to the problem, well, when your simple approach is not able to describe, for example, the experiments or what you observe and you are trying to explain.
Okay, no, thank you. So I have a question related to the title of your presentation. So you say that this model, how is it possible that this model can or this connectivity can be seen at different scales, from the micron to the meter to the, how is it possible that these kind of models can, if the physics are a bit different, the energy scales are different, the time scales are different, everything is different at different scales, you have this model that goes through all these scales?
Okay, so the model does not answer all the questions. What I'm saying is, or my key message is that it gives you an idea about the connectivity. How connectivity affects other things, this is up to other types of models and studies, and this might depend on the scale and things like that. But imagine the following process. I go to the kitchen and I try to do some gelatin. What am I doing? I take a bunch of ingredients. If you ask to someone from chemistry, they know about everything about the ingredients. For me, are just a bunch of grains. I put some water, but the water, the hot water, what we'll be doing is to promote, or it's to increase the temperature. And then when I cool it down, I mix it, I dilute it, and when I cool it down, I start to form bonds between the what were grains before. And eventually I get this structure that percolates my entire solution, that is a gel, and is this structure that I like to eat, and I like the properties, and I like to shake and see that it behaves like a gelatin, okay? And so the details, what is the temperature of the water that I need? What is the color of the gelatin that I will get? What is the flavor? Those type of things, you need other strategies to understand. And in particular, you go out of physics, you look to chemistry, you look to other types of things. But in general, this idea that as I increase the connection between the different building blocks, I end up having a structure that percolates, then this is something that I can fully understand with the percolation problem, with a purely geometrical model, and I don't need to add any complexity to that.
Okay, thank you.
You can find that for all the examples that I have said.
Okay, so you have another question from an anonymous. So is it the path that the termites take on the wood structure? Is it from, did they take the percolative aggregates?
Okay, so no, it's not the path. So in the case of the termite, what the termite is doing is eating or destroying the wood. And so what is key for the practical problem that I described of the wooden house is to guarantee that you still have connections between the parts that were not destroyed by the termite. And so when we think about the percolation cluster, where we want to have a percolation cluster is not from the parts of the termite, but rather from the counterpart, that is the region that was not visited by the termite.
Okay, thank you. So I have one last question. So this model is I think the sound is going. This model is a geometrical model. Are you listening? So this model is a geometrical model, so it's kind of a mathematical model. What is this condensed matter physics?
Sorry, I could not listen.
So why is this geometrical model or mathematical model, why is it condensed matter physics?
Well, the model itself is a model, so it's not condensed matter physics. What is condensed matter physics is the problems that we can tackle with this model. So what I'm saying is condensed matter, we are talking about emergent phenomena, or phenomena that emerges from the interactions. Here in this case, what emerges is this largest cluster above the percolation threshold. Even below the percolation threshold, you have some small clusters, but there's nothing special about those clusters. It's only when you go above the percolation threshold that you have something that emerges. And so you have disconnected blocks, units, and you don't have any emergent behavior there. It's only when you go above the percolation threshold that you see that the percolation cluster is emerging. Taking the example of the gelatin, is only when you form the gel, that you can eat it and you have something that is different from a cocktail of a drink made of some flavor. So we have some questions here.
Yes, no, we have some questions here. So one question from João Cordeiro. Do you believe that a great amount of physical phenomena can be described by the interactions of the system's components? So in the limit, can connectivity be the foundation of a more global theory of physics?
Well, well, Wolfram now comes with this weird idea that everything are networks. I don't buy that anyway. But when I say connectivity, or when I look into percolation, what I'm talking is interaction between the blocks and somehow correlations that can result from those interactions. And this is what I believe that for the systems that we want to look at, so many body systems, is where I believe that this plays a relevant role, is the correlations that result from the interactions between the particles. And in particular, the many body correlations that result from those interactions. And yes, this is something that is key when you try to describe this type of systems.
So we have another question from André Matias. Did you compare the results of the cube destruction with experiments?
No, not yet. So if you know of any experiments, I will be happy to see them.
Okay, so we have another question from an anonymous. So the question is about size. So since percolation is a transition for infinite systems, the size of the blocks is relevant. So does percolation really happen at different scales, or does it?
That's an interesting question. See that when I plotted the size of the largest aggregate as a function of the fraction of occupied bonds, I'm using parameters that are fractions. So in the vertical axis, I have the fraction of sites that belong to the largest cluster. And in the horizontal axis, I'm having the fraction of bonds that are occupied. But more than that, see that I produced the plot with different lines for different lattice sizes. And this is something that we need to do when we do numerical simulations. We really need to study the impact of the system size on the results. And so what you can see is that if you think about a finite system, if you have bonds between the particles, obviously you have an aggregate even below PC. But what is so interesting about the percolation model is that when we see how the largest aggregate scales with the system size, it goes sublinear with the system size. So yes, you have some degree of aggregation between the blocks, but it's irrelevant at the macro scale. Even in the best case that I'm showing you here, I have 4,000 times 4,000 sites. Nothing compared with Avogadro number that is 10 to the power 23. So what we are really interested in understanding is what happens when we go to the limit, the thermodynamic limit that is the infinite system size, where you consider an infinite number of sites. And what you are seeing here is that when I rescale by the system size, the behavior that I was describing for values of P above 0.5 is the same and is observed at all these different scales. So even in the infinite system, you will have a cluster that spans the entire system, provided that you go above this critical value of the fraction of occupied bonds.
Okay, so we have another question from an anonymous that asks if the percolative aggregate, is it the fastest way from one side of the network to the other?
Okay, is the only one. Okay, so there was a huge discussion, and there is a theorem by Schuster and Wagner. It's a theorem by, I forgot now the names, but a theorem that says that at the percolation transition, depending on the dimension, or in a percolation problem, you only have 0 infinite clusters, 1 infinite cluster, or an infinite number of infinite clusters. And you only get an infinite number of infinite clusters at PC for dimensions larger than 6. That is the upper critical dimension of this problem. I will not enter into the details. But so there is only one cluster connecting one side of the system to the other. At least when I look to the thermodynamic limit to the infinite system. And so is that cluster that there is all the possible paths, and there are many possible paths, especially as you move away from p equal to 0.5, that take you from one side to the other, but all those paths are part of the infinite cluster, or of the largest percolating cluster.
Okay, Nuno, so we have another question from an anonymous. So you mentioned that you could not find experiments for the cube destruction. What is the difficulty of making that experiment?
Well, I'm not aware of someone that has done the study. I know that is a practical problem, for example, for hood houses. I think that the difficulty here is to have a certain degree of control over the particles that are moving inside and destroying the connections. Okay, I have seen suggestions based, for example, on enzymes that can activate or deactivate bonds between the particles, but I have never seen a systematic study where people focus on the percolation properties of these systems. So I don't know if there is some experimental challenge, but as far as I understand, or as far as I know, there are no results.
Okay, so Nuno, we don't have any more questions. I think we can thank you for your presentation and for answering the questions. And we'll have another webinar tomorrow. I hope you be able to come. Thank you, Nuno, and goodbye to everybody.
Goodbye to everyone. Bye-bye.